This is reading week 11 for Physics 2212. The first thing we learned about this week was how Faraday's law can be used for current carrying coils. Coils are basically multiple loops of wire that are connected and modeled as such. We see how they can be applied to some of the concepts we learned last week about loops of coils. For example, the electric field will still wrap around the coil. This is something that I already knew would happen based on what we learned. We can then break it down by each individual loop to get the total EMF, which is the number of loops n times the absolute value of d phi b over dt, which is the derivative of the magnetic flux. And another thing that we already knew was that I equals EMF over R, so we could then apply our new expression for the total EMF for the coil to get the induced current of the entire coil. Next, we talked about an application in which there are two coils, one with a power supply and another right below it. I did not know how to approach this problem at first and found it to be quite confusing, but referred to the student wiki to find some more examples of what these problems look like and sort of how to approach them. And the first step was to take the B field at the second coil, the one below the one with the power supply, assuming it's on axis and uniform, then find the magnetic flux for a single loop and use that to get the total EMF for the coil. Using that, we can find the current as explained on the previous slide using EMF over R. In the second video, we learned about solenoids. Solenoids have a radius much smaller than that of the total length of the set of loops. This is what sets them apart from just coils. And the direction of the current will be into the page at the top of each loop and out of the page at the bottom of each loop. I was curious about how the direction would change through the inside of the solenoid, and what we did know about the inside of the solenoid is that the magnetic field can be described using the constant expression of B equals mu naught ns times I over ls, and my question of the direction was answered by the right-hand rule, which can be used for the inside of the solenoid. We can apply Faraday's law to find the current for a solenoid with a current inside of the coil. We follow the steps for finding the expression for B of the solenoid and then finding how it varies with time. And for the single loop, so we can find the magnetic flux and how that varies with time, and then find the EMF and apply that to I equals EMF over R. And finally, we can use Lenz's law to find the direction of that current. In the case where motion of a bar is involved, we can call this motional EMF, and we can alter the magnetic flux derivative to account for this change in area. This can be done by multiplying the constant B field by the width and the velocity with which the bar is moving. We can then find the magnitude of the current and the direction using Lenz's law and the right-hand rule. I thought that this was pretty confusing, especially in terms of the problem solving, but I found this example from the student wiki that kind of stepped through the problem solving, and it really helped my understanding. Lastly, to relate this to my major of environmental engineering, work solenoids can be used in an array of household applications, and I found a paper that investigates the environmental effects of how they are produced, and one of these effects is sort of how and where production materials are sourced.